Okay, my name is Nicholas Elsesser, and I'm going to be talking about my linear programming project for this semester, which was AC optimal power flow relaxation as a linear programming problem. And so just a general outline of what this presentation is going to be. So we're first going to go through the motivation of what is solving a power flow problem in the first place. The next thing we're going to look at is how do we build an electric grid network, and then what does it mean for power to be balanced on that network. Next thing we're going to look at is the AC power flow equations. So those are the physical equations derived from Ohm's law. And then the next thing we're going to be looking at doing is taking a linear relaxation of those AC power flow equations. And then we call those the DC power flow equations, which despite the name have nothing to do with DC current, unlike the AC power flow equations, which are derived from the nature of the AC current. So the next thing we're going to do is to make this an optimization problem, especially a linear program problem. We need to be able to write it in matrix form. So we express these DC power balance or DC power flow power balance equations in matrix form. And next, we look at expressing those power balance equations using linear programming. And then finally, we have some implementation results and then conclusions. So our motivation, what is power flow? Optimal power flow is generally used to solve a generator dispatch problem. So you can imagine we have an electrical grid. And so there's loads on the electrical grid, and then we need to find the correct amount of generation needed to satisfy the load on the grid at any given point in time, but we're subject to the physical constraints of the grid. So the way that the grid is actually built. And so we can model these physical constraints using nonlinear AC power flow equations. And so when we model it this way, we end up with a nonlinear, non-convex model that's slow and expensive to evaluate. However, the results are accurate. And so we can simplify those AC power flow equations into linear equations and call that approximation the DC power flow. And so since then the equations are linear, the optimization problem is convex, and therefore it is really fast and really cheap to evaluate. However, it's not as accurate. It's an approximation of the actual physical network behavior. And so generally, you're looking to solve both the power generation, and then also like we have these voltage angles and voltage magnitudes at each node in the network, are essentially we tune how the power flows around the network using those two parameters. And so those are generally our decision variables. That's how the regulators that decide which generators turn on and off, they solve these optimal power flows of the dispatch problem. However, our problem is slightly different. We're taking historical data where we know what the generation load actually is, so we're not finding the correct generation. And then we want to be able to recover sort of these voltage angles and voltage magnitudes on the network, so we can reconstruct what the power flow looks like on the network at the lines. So the power flowing between the lines rather than the generation and the load is what we're interested in. And so we'll call this the optimal power flow recovery problem. And so moving on, how do we actually build an electric grid network? So our network that we're looking at is made up of buses, which are the nodes of the graph, and then we have branches, which are the edge of the graph. And so buses are essentially collections of generators and loads, and they can also be empty collections of generators and loads, so they can be passive, essentially, just as sort of like a node in a graph. Or there can be multiple generators and multiple loads at a single bus. And so then our edges, we have lines and transformers. And so each line and transformer is a unique connection. So a line can only go from one bus to another, and then a transformer can only go from one bus to another. And the lines and transformers only go between buses. generators and loads are sort of aggregated on a per bus basis when we're solving these problems. And so we're solving a flow problem, a power flow problem. And so what that means is that the flow into each bus must equal the flow out of each bus. And so you can see in these equations on the left, we have we have two sets of equations. That's because we're dealing with AC current. So we have a real power flow and a reactive power flow. And the reactive power flow essentially comes out of the imaginary numbers that you get into when you have an oscillating AC current. And so we have these on for each of those equations. On the left, we have the inflows. Essentially, we have the generation marked with these superscript G nodes, or the superscript G. We have the power coming in from the lines marked with the superscript N. And then we have the power coming in from the transformers marked with the superscript M. And then similarly, we have the power flowing out. That is the loads power flowing out across the lines and power flowing out across the transformers. And so we can see that these have to equal 0 in order for the power flow problem to be solved adequately. In the real world, if this is not solved correctly, then we get really strange or really bad issues, instabilities with the network. And so we were given the loads and the generation, but we have to solve for the flows across the lines and transformers. And so these are those AC power flow equations that are derived from Ohm's law. And so it's really clear. And you can see our decision variables here are the voltage magnitudes and the voltage angles. So we dropped the power generation is not a decision variable. Like we said, it is constant. And so you can see that we have these really nonlinear terms for both of our decision variables. We have these quadratic terms with our voltage magnitudes, and then these sinusoidal terms with our voltage angles. And then we also have these other terms that describe sort of the properties of each line or transformer. So we have the conductance and the susceptance, and then we also have the winding ratios for the transformers and the phase shift angles for the transformers. And so these equations are, messy, pretty intense, and obviously not linear, and just very painful, clearly then to solve. And so that motivates then we need a linear relaxation to make this problem a lot easier to solve. And so we make these 5 following assumptions that allow us to greatly simplify the power flow equations. So the first thing we do is we drop making the voltage magnitude decision variable. We say that it is constant for all of the buses in our network. And then in practice, we actually do this by estimating from data points, is how we did this in our implementation. And so the next thing we assume is that the magnitude of our change in angles over our branches is small, and therefore we can approximate the cosine of this angle as 1, and the sine is roughly this angle. And this works because that magnitude is small. And so then next thing we assume is that the branch conductance is 0. So that gets rid of those G sub K, K prime terms. And then we assume that our transformer phase shift angles are 0 and that our transformer winding ratios are 1. And this kind of makes our transformers, essentially turns them into like lines pretty much. And so when we do all that, we can simplify the AC power flow equations, and we find these simplified DC power flow equations, which are linear, and we also get rid of our imaginary terms. And so going forward, we can then drop our imaginary reactive power terms from all of our power balance constraints, since we can't control them anymore. And so next, we need to be able to formulate these equations into a matrix to be able to solve it easier with linear programming. So, and so the first thing we do is take those, here we just show it for the derivation for the line expressions, but the expressions for the transformers is pretty much the same. So what we first do is we have these adjacency matrices that take us from a bus to a line. Essentially, we denote each line as a directional edge with the starting bus and the ending bus. And so then we have these two adjacency matrices to kind of create that data structure. And then we're able to express our power or DC power flow equations over the lines in this form. So we're able to eat the susceptance terms are placed in this diagonal matrix. And then our voltage angle differences are calculated using these adjacency matrices with our decision variables that are these voltage angles. And so this gives us the power flow on a per line basis. However, we're interested in solving this on a per bus basis. And so then we use our adjacency matrices again to get us from sort of this line space to this inflow outflow of the bus space. And so we can take these terms then and then plug them into the original power balance equation. So we first take these terms that are, we combine our like terms, and then here we just look at the line power in particular. And so we can expand and rearrange these terms, and we find that we can express this all as like a really big matrix to sort of kind of convert us or define the power flows and then convert us back into the bus power flows, input and output. And so we take this large matrix and we can just simplify it by calling it N for the lines, and then the similar derivation leads us to an M matrix for the transformers that you can see below the N matrix. And then you also notice that we introduce this A subscript or superscript N or superscript M, and this is essentially a parameter we use to control the activations of lines or transformers. So this allows us to essentially do sort of sensitivity analysis with our model that allows us to turn lines on and off in the future. And so then we can simplify our original power balance equations by moving our load and generation, which we are given, over to the right-hand side, and then simplifying our line and transformer powers into this expression you can see here. And so moving forward, we put this into a linear program. So we, this is clearly a linear regression. We can't solve it exactly because it's already an approximation by definition. And so conveniently, we can solve this as an L1 norm, and it makes it really easy to pose it as a linear program. And then also solving as an L1 norm promotes sparsity in our solutions, which is desirable because sparsity in our case represents sparsity in the residuals. So it sort of minimizes where there, not only will it minimize the total sum of the error in the power flow on each node, but it will also sort of make sure the power flow on, or the error in power flow on nodes is zero where it can be. So we want that sparsity promoting effect. And so then we also bound the range of the voltage angles negative pi to pi, as it's like a periodic term. And so we can, again, simplify some of our matrices just notationally, and then we can express this L1 regression as a linear programming. It's pretty straightforward. And so then we also propose this modified DC optimal power flow recovery. So essentially, in this first one, we're trying to minimize our error terms. However, we are allowing our voltage angles to be whatever within this range of negative pi to pi. But one of the key assumptions we're making to relax these is that the differences between our angles is near zero. And so we can do in a soft enforcement of this relaxing assumption by essentially penalizing, since our voltage angle differences are linear, we're already finding them, you know, in these earlier derivations of our matrices. We can simply penalize those terms as well using the same L1 regression. And so we have these results for both the initial and then our modified DCOPF recovery algorithms. And so you can see the effect that, and these are implemented on a real world ISO grid, the PJM ISO grid, which has around, you can see the number of buses and generators. This is a pretty large scale system. And then, so we can see on each of these graphs, we're comparing here the voltage angles because those are the decision variables we're solving for. We can see how we can see the distributions of our voltage angles by themselves and also the differences between our voltage angles. And so it's interesting to note that between when we add that extra penalty term onto the voltage angles, we can see that both the voltage angles themselves and also the change in angles decreases significantly in magnitude. You can see that distribution is a lot tighter. You can see before we added that penalty term, we were getting changes in our angles that were, well outside of, reasonable approximation. And so adding in that penalty term brings it down. But we can see from this table down here, which measures our average error, our median error, and then our percentile errors for our residuals in terms of the power balance. We can see that adding those extra constraints significantly increases the error in our power balance itself. So we have to sacrifice some power balance error to bring in sort of this, to make our relaxation assumptions a little bit more valid when we're actually solving, bring some of the structure back into the problem. And so then finally, we also have, we ran an AC power flow recovery on this same data set. And so we can see that the change in angles is actually really similar distributions between the modified, so when we add in that penalty term, and then the ACOPF. However, the actual angles themselves are kind of different. They're offset a little bit, which is interesting. That's probably, I'm not 100% sure why, but it's probably due to the nonlinearity in the original system of equations. And so we can also see the DC optimal power flow time is orders of magnitude faster to solve than the AC optimal power flow time. And this is again because it's linear and convex versus nonlinear. And so our conclusions, we were able to successfully derive a DCOPF recovery model from our ACOPF recovery model. We're able to express that recovery as an L-run regression, which we can express as a linear programming problem, which makes it simple to solve. And then we implemented a model on a large scale network and we're able to compare with our AC optimal power flow results. And then we also saw that when we add in this term to penalize sort of this violation of our relaxation assumption, we get results that conform to our assumptions. However, we then sacrifice some of our approximation ability to satisfy our original constraints. We need more slack. And so for future research, it'd be interesting to see if these solutions from the DCOPF recovery are good enough to be used as a warm start to an ACOPF recovery problem. So if we're doing some sort of sensitivity analysis, we're running a lot of optimal power flow problems, we want high resolution. If we can save even a few percent each time by using a DCOPF solution as a warm start to the ACOPF solution, if each ACOPF solution on a cold start takes 100 seconds and we're saving a few percent each time, then over hundreds of simulations, that saves a lot of time. So that's an interesting research path to go down using these models. And with that, my presentation is done. Thank you very much for listening. And I also have a GIST link, GitHub GIST link to the code in the description of the video. Thank you very much.